All right. So, well, I have sent you an email with instructions to get the project started for today. You know the drill already. You can follow the instructions on the email, but basically I uploaded a new PowerShell script we're going to be working with today to GitHub. So you first pull that, and then you create your project first on GitHub, clone that, create your subfolders, move or copy this PowerShell script into the code folder. And then the data, I did not share the data with you because it's basically the data that we all created on the 09 project. So basically, I'm asking you to copy the data from that project and paste that into the data folder of today's project, which is the ElasticNet exercise. While you're doing that, I'm going to get started mostly because today's lab actually starts with a lot of explanation of the algorithm we're going to be training today. So I'm going to get started with that. And then you can, as you catch up, creating the project and moving files. So I'm just launching here my RStudio project for today's exercise. All right, so today we're going to be training our first machine learning model. And the one I want to get us started with is ElasticNet. So especially here in Athens, I can more easily see you. Can you raise your hand if you have either heard of, used this model, or have some experience with ElasticNet, Lasso, or Ridge models? Right, at least here in Athens, nobody raised their hands. So I guess that perhaps is a good thing that you're gonna all be learning something new today. All right, so our learning objectives of this exercise are to understand linear regression penalization types. We're going to talk more in detail about what that is and what I mean by that. And then we're going to use our machine learning framework to pre-process data, train an ElasticNet model, and evaluate model predictability. If you recall, if you were to go back to the lecture and the slides that we went through last class, you're going to see that every single step that we talked about in the lecture, we're going to be implementing in this exercise, but at every machine learning exercise that we do. So the framework is very similar. There are going to be a few changes as we go from one model to another, but the overall framework remains very similar. So just for you to keep that in mind, again, one of my goals in this class is to teach you in a very structured way that helps you to take what you learn here and apply it to data that, it's not what we do in class. So maybe your own research data. So we're going to be using that framework. And I just wanted to make that connection between what we're going to be doing today, what you saw in lecture, and also what you're going to see in the future exercises with other models that are going to be different from this one. All right, so first off, so a few things here overall, just for you to have an idea. I'm going to be teaching you in class 3 to 4 machine learning models. There are many more than that. And we could not cover them even if that was the only thing we did in the whole semester. So my goal here is not to say, these are the models that you're going to use and that's it. My goal is for you to learn the process. So if you want to learn other models, different models in the future, you have the skills and the tools to do it on your own. So overall, a few things that you're going to notice throughout our machine learning exercises are things like, first, you need to understand what is the model doing. So that's how we're going to start every single machine learning exercise. I'm going to talk first about the model, just the theoretical implementation of that model, how it works, what are some key hyperparameters of that model that we have to be aware of and fine tune in our training process. So knowing the model, how it works is the first step. Knowing what overall hyperparameters it has is going to be another one. and then just how we're going to go through this and train the model overall. So really knowing what the model does and what key hyperparameters it has are things that if you want to learn any machine learning model, that's what you would need to know, and then how to implement that in this case. All right, so start talking about here, what is the problem we have? So we went through the multivariate exercise where you saw that linear regression models can suffer from multicollinearity. ElasticNet is a linear model, as you're going to see soon here. And again, multicollinearity is this problem where it happens when you have two or more predictors that are highly correlated, not with your y variable, not with a predicted variable, but just between themselves. So two x variables on that right side of the formula are highly correlated. That has an impact on your model performance. We also already talked about that there are some methods that we can use to overcome multicollinearity. So that includes things like dimensionality reduction using principal component analysis, something we already did and talked about, and or variable selection. That could be by hand. As far as what I mean by that is you giving the model the variables that you truly believe or have scientific backup of the reason why that X variable impacts your Y variable. Right? This could be based on the literature, it could be based on your experience, could be based on crop physiology, physics, whatever it is. Also, we can do variable selection by using models that do variable selection for us, which is going to be the case of today that we're going to learn with this model. If you're using a model to perform variable selection for you, one way of doing that is through a process called regularization, where we basically apply penalties to the model in a way that it keeps important variables and removes unimportant variables. That is what we're going to be doing today. We're going to be using a model that performs variable selection by applying penalties and regularization to the model overall. All right, so let's start talking about that. What does that mean, and how does that actually look like when you're applying these penalties to a model? So in linear regression overall, which again, today's model is a linear regression type of model, our model coefficients are basically estimated by minimizing the sum of the squares of the error. We kind of saw this on the ANOVA setting where we're talking about mean sum of squares and sum of squares and one of those was the error. But basically what the sum of squares of the error is the sum of the square differences from the observation and the regression line. Or in other words, the observation is what you observe, the regression line is the predicted value, right? So in this case here, we're just seeing something that is not our data, but it's basically using, I don't even know what this X variable is, but it's like GR BLIV area. I'm not sure what that is, but that is the X variable explaining the sale price of a house. As you see, all the points, all the red points are just that scatter point. There's the scatter plot between this X variable and that Y variable. Then we have the blue line here, which is the best fit line that minimizes the sum of the squares of the error. What does that mean? There's only one line. So if you look here, if you were to take this line and just tilt it a little bit up, tilt it a little bit lower, none of those new placements of this line would minimize sum of squares of the error. The solution where this line here minimizes the distance between each point and the line, there's only one solution for that, which is the line that we see, which is the blue line. That is basically what any regression model is trying to do. It's trying to take, imagine you fit any line here, it takes the difference for all the points to the line and tries to minimize that distance. So there's only one solution where this line here minimizes overall the distance between all points in the line. That is how basically regression is happening behind the scenes. This is our loss function, is minimizing the distance of all points to the line, and there's only one solution to that. There's only one line that minimizes the sum of the squares of the error, which is normally or most of the time, this is going to be our regression line. That's what we see. So overall regression models, when we are looking for the intercept and slope, those values of intercept and slope, there's only one combination of those two values that minimize the sum of the squares of the error. So for every regression model, our loss function, or what we're trying to optimize, is to basically minimize the sum of the square of the error. Now and that's just for linear models in general. But in regularized linear regression, we apply some penalties to this function that the model is minimizing sum of the squares of the error. We're going to apply some functions there. So when we apply penalties to the minimization of sum of the squares of the error, the coefficient of unimportant and or correlated x variables get constrained, reducing their influence in the model. So that's basically, we're going to be looking for a penalty that we can implement to that loss function, which is to minimize sum of the squares of the error, to basically kick out some variables or reduce the influence and or kick out some variables that are unimportant or correlated in that model. We're going to see some examples more visually here, just so it helps you understanding. There are basically, I guess, two penalties that we can implement, and then the combination of them would be the third case here, where one of them is called ridge regression, that applies a ridge penalization. There's a lasso regression, which applies a lasso regularization or penalty. And then there is something called elastic net that combines the penalties of both ridge and lasso into one model. So if you were to go to the literature or even to a paper that is using these models, they may be only using a ridge regression model, or maybe only a lasso regression model. Or maybe they're doing elastic net, which combines all the previous two. Just to tell you that we could run each one of these individually if we wanted. I'm going straight to running elastic net just because of time constraints and because I think this exercise can give you some idea of how elastic net is using both a lasso and a ridge penalization together. However, on your side, or when you read literature, you may see papers that use only ridge or only lasso and don't use elastic net at all. All right, so let's start talking about these penalties. What are they and what are their influence on the model? So the first penalty we're going to be looking at is the ridge penalty, which if you use a ridge penalty, you're running a ridge regression model. So the size of this penalty, which is referred as L2, can take a wide range of values and is controlled by the tuning parameter lambda. This is a key component here. Every time that you hear there is a tuning parameter, it means that the value of that parameter can take different values depending on your situation, depending on your data. And it's not something you can go, I mean, you can say, well, let's use a lambda value of X, whatever you want to decide, but that value may not be the best value for your data. So that's where we have to train a model to learn what is the best lambda value for our model. Just to also show you all here. So this is basically markdown language. So on your scripts, I think if you hover over here, it's going to show you the equation below. We have not talked a lot about this in Quarto files or R markdown files, but one of the cool things is that you can use markdown language to write equations, especially. So people that publish in journals that are really focused on a lot of equations like statistics and math and physics and things like that, they a lot of times they publish papers out of a markdown file, which Quarto is one of them, because it helps them to write all these fancy mathematical notation. So this is just a plus, I guess, that we haven't really talked much about. But my goal is you don't really need to focus on the markdown itself. Or the LaTeX itself. What I want you to see is more the equation that comes below it. All right, so with a ridge penalty, the penalty is called L2. And as you can see here, that penalty is applied to the loss function of a normal regression model. So a normal regression model would be minimizing the sum of the squares of the error, period. Here we add a penalty to this function. So now there is this penalty happening there that's going to impact how this minimization of sum of squares of the error is happening. And then, so L2, this penalty here is basically, there is a lambda value. So again, this value here is what we're going to look for, is what we're going to train our model to decide what is the best value for this data. And then that's basically multiplied by the sum of the beta j's. So beta j is going to be the different slopes you have for different variables. So imagine that we have a model that we're using strength explained by all 74 weather data or weather columns that we created already. Each one of them is going to have a beta, which is basically the slope for each one of them. So we're taking all the slopes for all the variables that you have, all the predictor variables in your model, and then just multiplying them by a penalty, which is lambda. If lambda is 0, there is no effect, and our objective function equals the normal. So imagine if lambda is 0, then is 0 times the sum of the beta j's, meaning that this whole thing goes to 0. So if L2 is 0, then you put a 0 here, it becomes the same model as a regular regression model. There is no regularization if lambda is found to be 0. However, as lambda increases to infinity, the penalty becomes large and is going to force some of those coefficients towards 0, but not all the way. So this is basically a depiction of that. So imagine here on this figure, we have, I don't know, like each line here is representing the slope of a different predictor variable. So imagine that each line here is maybe temperature in September, and then temperature in August, and then solar radiation in a given month. Imagine each line here is representing the slope associated with a different predictor variable, a different x variable. So we have that coefficient, what the coefficient here, the coefficient value on the y-axis is basically the slope value for that variable in the model. And on the x-axis, we have lambda going from, well, I guess 0 all the way to 10,000. The value of lambda is changing here. So what happens is if lambda is 0, which is what you see, like if you were to look vertically on this plot, that would be the coefficient, the slope of each one of these variables would be that. So you see that some are greater than 0, some are lower than 0, and some are really close to 0 already. As lambda increases, notice how some of those variables are, the coefficient value of different variables is being shrunk towards 0. And this shrinkage is happening both to basically make the importance of that variable lower in the model, and also it's doing that in a way that is controlling, is forcing. So if there are two highly correlated predictor variables, one of them is going to shrink first, and it's going to go really close to 0, whereas the other one is going to remain with importance in the model. If you push lambda all the way, everything is going to go really close to 0. So this is what we need to find. What is the lambda value that we need to use in our data, in our model, that shrinks enough correlated variables, but not all of them? Because we still want them, we still want this model to be able to predict something, so it has to have some variables that remain in the model. So let's say if you were to take a lambda of 10, I guess what we're seeing here is that variables x2, 3, and 5 already lost some importance in the model. We see that their coefficients already shrunk a little bit. And also variables x1 and x4. Well, variable x1 actually increased the absolute value of the coefficient actually increased. I mean, it is on a negative scale, but it went from about minus, let's say -7 to almost close to -10. So this x1 variable actually increased importance in the model and then starts shrinking as well. Also, we noticed that different variables get closer to zero at different lambda values. So these variables that have a positive coefficient, they get close to zero, which is this line here. They get close to zero before these variables that have a negative coefficient. So that is kind of controlling, again, the impact that each one of these variables is having on the model that is predicting a given y variable. Before I move on, I just want to make a quick moment here to check in with you all. If anyone has any questions, or maybe this is not clear. All right. Maybe I explained really well, or maybe you're all very confused. One of the two. All right. So one thing here, though, is that, so we're looking into the ridge penalty first. One key difference of the ridge compared to the lasso penalty is that ridge does not perform variable selection. Or let me say that differently. Ridge does not set any coefficient to zero. It only brings them really close to zero. So let's say it would be 0.0001 would be the slope, but it's never actually zero. So one of the benefits of using a ridge regression is that you still retain all your variables. You just force some of them to be more important than others, but they're all still in your model. And so if you believe that there is a need to retain all of your X variables in the model, but you still want to reduce the effect of multicollinearity and the noise that creates in your model, maybe ridge is the best for you. So you're still keeping all those X variables. None of them are being excluded, but some of them are losing importance because they have their coefficients being shrunk. However, if you want better interpretation out of the model, and you know that some features are redundant, that you don't need all of them, perhaps using a lasso, which is the next penalty we're going to see, or an elastic net, which combines both ridge and lasso, would be preferable. All right, so now let's talk about a lasso penalty. So a lasso penalty is so lasso stands for least absolute shrinkage and selection operator, but people refer to it as lasso. So implements an L1 type of penalty. And the way that that looks like is still is going to be a penalty that we're using on that function that minimizes the sum of squares. So remember that every regression model is minimizing sum of squares. Here we're just adding a penalty to that function, and in this case, the penalty is called L1. It's a lasso penalty. If you hover over this LaTeX code here, you're going to see the actual function. So what L1 is doing is it also has a lambda here, but now it is multiplying that lambda by the absolute value of the coefficients of the beta j's of a regression model. This is the difference between, mathematically, this is the difference between an L2 and an L1 penalty. The L2 penalty was just using the value of the coefficient, whether it was positive or negative. It was allowing that direction to be a play, whereas an L1 penalty is using the absolute value. So if it is minus 0.1, it's going to turn into 0.1 in this form. So while the ridge penalty, which is the first one we saw, is bringing or shrinking some of the coefficients to be near zero, the ridge never sets them to zero completely. The lasso does. So lasso penalty here have the potential of setting completely coefficients to be completely equals to zero, which then is doing variable selection for you. So variables that are related to coefficients that are completely set to zero are basically out of your model. They don't have an effect on your model. So a lasso penalty here, the L1 penalty, will push coefficients all the way to zero and therefore do variable selection for us, like we see in this figure. So the same way we have coefficients on the y-axis, we have lambda, in this case, the lambda for L1 for lasso on the x-axis. And we see that as we increase the value of lambda, some variables are losing their importance. So let's say if we look at this variable x4, its coefficient is being shrunk. And then at this lambda here, whatever that is, let's say it would be, I don't know, 0.5 maybe. X4 is completely set to 0. The coefficient of X4 is completely set to 0, meaning that that variable is just removed from your model. It's not there anymore. So Lasso does set coefficients all the way to 0, and therefore performs variable selection for us. Yes.
Is there a reason that the scale for lambda on L1 versus L2 is so different?
That's a great observation. So Jonathan's asking if is there a reason that for why lambda on this figure, the range of values for lambda in this figure is different from the figure above? Yeah, so basically here, I mean, what we're going to be working in the model, we're going to see that lambda for L2 for us is going to range from 0 to 1 in our implementation of it, whereas lambda for L1, which is what we're looking right now for Lasso, is going to range from 0 to 1, and lambda for L2, which is the first one we saw. I know it's a bit confusing of the ordering there in the name, but lambda for L2 really does not have a limit. It goes to infinity. So that's a great observation. But they're basically two different lambdas. I mean, that's perhaps another confusing term because they are both called lambda, but right now we're just seeing them independently in their own models, and that's why they're both called lambda. But really, one of them, when we bring into ElasticNet, we're not going to call both of them lambda. They're going to have each one, they're going to have, so L2 and L1 is what we're going to call them. So they're going to be, we're going to be able to differentiate between the lambda coming from Lasso and the lambda coming from Ridge, which is going to be the ElasticNet is going to be a mix of both. So switching to the Lasso penalty, the L2 penalty we're seeing here, not only improves the model, but also conducts automated variable selection, because again, it's going to take variables that are not as important and also variables that are correlated and set them to 0, set their coefficient to 0. All right, so if you combine both of them, both of those penalties, L2 and L1, you get ElasticNet. Why would we do ElasticNet? So, well, first, before we'll talk about why we're doing ElasticNet. The way that is implemented in the model itself is that now we're minimizing the sum of the squares of the error plus the penalty from Ridge plus the penalty from Lasso. So you're bringing both of them together when you're minimizing sum of the squares of the error. But why would you do that? In which cases is that going to be important? Even though the Lasso model does perform feature selection, it still suffers a little bit from when you have two highly correlated X variables. And so sometimes it may push, so if you run the model one time, it may push one of those variables to 0 first. And if you run again, it may force the other variable to 0 first. So it's not very systematic about which one of the correlated variables it is setting to 0 first in each different run of the Lasso model. So using the L1 regularization that we just saw. In contrast, the Ridge regression penalty is a little more effective in systematically handling the correlated features together. So by using Ridge, it's going to be better at setting one of those correlated variables very close to 0 first. But remember, the difference is that Ridge does not set variables to 0 at all. It brings them really close to 0, but it's never completely 0. Whereas Lasso does set them to 0. And Ridge is better at more systematically choosing one of those correlated variables to bring close to 0 in a more consistent way, and not just somewhat arbitrary which one of the correlated variables is brought close to 0 first. So the advantage of using ElasticNet is that we have a really good effective regularization through Ridge. So Ridge is going to be more consistent of which variable is being brought closer to 0 or having its coefficient being brought closer to 0. However, Ridge does not set anything to zero. So we need Lasso then to be the big regularization that's going to say, all right, so Ridge brought some variables close to zero in a more systematic way, but now we need Lasso to say, let's set those to zero as well. Lasso is the one that really tells you or tells the model which variables should be set to zero or have their coefficients be set to zero. So combining both of those features of Ridge being more systematic and Lasso being able to do feature selection into one model, that's what we're doing with ElasticNet. It's combining both of those features. So here we have another plot that is similar as before, where we're actually applying ElasticNet. So it kind of looks, it has, if you were to look at this in comparison to the two previous ones, you would see that it resembles, it has some resemblance to each one of them. So we're still bringing variables close to zero and systematically which variables are being brought close to zero by Ridge. And then when they get close enough to zero, Lasso then comes and sets them to be completely zero and therefore doing variable selection. So for example, if you were to have here in this case a lambda that let's just choose maybe a value that would be here. Maybe this would be, I don't know, 8 or 9 lambda. What would happen at this point is if you use a lambda of 9, the only two variables still left in the model would be x1, which is this, and x5, which is the pink one. All the others had already been shrunk to zero by Ridge and then set to zero by Lasso. So basically, they're working together in an ElasticNet approach. All right. Any questions about this? Because this was basically us talking about the model implementation, the theoretical implementation of it. The next step, we're going to start coding. So I just want to make sure that if there are any questions, that we can go over them now. Okay. I don't hear any, so let's get going. So if you come to the next chunk, as always, I have some setup for you. We're installing 3 packages that I don't think you have yet. So as you know, just uncomment, run just that line of code, comment it off after installs or delete the line, and then do so for GLMNet, VIP, and Tidy models. I think maybe Tidy models can take a little bit longer than the others, but still you should be able to do it successfully. While you're working on that, I'm going to keep going here because we're going to start very slow. And so if anyone has issues installing, feel free to let me know. We can stop and check it out. But if not, I'm just going to keep moving here. So after you install the packages, make sure you run this chunk. Well, after you install the packages and comment off and or delete the install.packages lines, go ahead and run this chunk so we can actually load those packages. And just as a quick heads up, so GLMNet is the package that we're going to use to implement ElasticNet. VIP is a package that's going to help us to look into variable importance across different machine learning models. And Tidy Models is a family of packages developed by Tidyverse that help us implement machine learning workflows in R, where each package has a different role in this workflow. All right, I think so. If you did what I asked you to do as far as going to the project 9, where I don't remember what we did there, but it was project 9. On the data folder of that project, we had exported the weather month sum.csv from one of our previous exercises. I asked you to basically copy that code from there and paste that code into the data folder of this project. If you did that, then this path would work for you. If you did not do that, then you're going to have to do it for this to work. But if you run this, it's just going to import our data frame, which if you remember at that level, we had 698 rows where each row is representing one site year. We have 75 columns where we have year and site, so our descriptor columns. We have strength GTEx, which is cotton fiber strength. That's our predicted variable. That's what we're trying to predict. And then we have all the other weather variables as columns. So the mean or the sum of different variables for different months. Each one of those combinations is going to be a column. And we already saw this. So you should be familiar with this data frame by this point. All right, so let's start using the workflow that we talked about in class and implement that in the code. In R, we're going to be using many packages that were built specifically for machine learning in R, and all of them are going to follow the same tidyverse concepts and principles that we've been using. So they all follow a very similar argument structure. They all are, I think they're all pipeable as well. At least the functions we're going to be using are all pipeable, so it's easy to combine a pipe workflow. So they all work together very nicely. And these packages, all these individual packages, they are made available through a bundle called Tidy Models, which is what you just installed. So remember, we have Tidyverse, which is a family of packages that includes dplyr, ggplot2, readr, other packages that are part of the Tidyverse, and then Tidy Models has different packages that are specifically developed for machine learning. So again, this meta package is called Tidy Models, and inside of Tidy Models, we have the packages rsamples that help us to do data split and resampling, the package recipes for data processing, package parsnip to specify model types and engines, package tune, which is going to help us to fine-tune hyperparameters, package dials to help create grids, and package yardstick to assess performance. So I hope that as you're reading through this list, you may be identifying that these steps are what we talked about as part of the workflow of any machine learning exercise. So we have here individual packages that will be helping us with functions to handle the different steps. All right, so let's start coding here. So the first step, as we talked about in the lecture, is going to be pre-processing. There are going to be two things that we're going to do at pre-processing. One of them is data split. The other one is just pre-processing steps to our data frame that we may need to do, especially for different algorithms. So the first thing, let's do data split. We're going to use a 70% training, 30% testing first. Before you run like the whole chunk. Well, I guess maybe we should code and then run the whole chunk. But I just want to tell you that we're setting seed here. Have we talked about setting seed in this class? Okay, so you know what that does is basically making sure that our results are reproducible because you're going to be doing a random split. If you do not set seed, each time you run this chunk, you get a different split. You get a different set of data going to training and going to testing. So set seed is just making sure that we get reproducible results. So next, here on this weather splits, this is where we're going to start doing our data splits. We're going to give it assignment symbol. We're going to use a function called initial underscore split coming from the rsample package. We give our data object, which is called weather. And it has an argument for prop, which is the proportion that you want to split. Basically, the proportion you want to go into training. Of course, whatever is left of this proportion then goes into testing. So let's use 0.7 to represent our 70% training. If you run this, and then you just print weather splits, it looks weird because at this point, it does not look like a data frame. It's just telling you what's going to happen with your data. So it's going to say that you have a total of 698 rows, and then 488 of those rows are going to go into training, 210 are going to go into testing. This is basically what's telling us at this level. Now, on the next chunk, we're basically going to retrieve those 488 rows in training and 210 in testing and assign those data frames to their own objects. So if you come to weather train, let's give it the assignment symbol. We're going to use a function called training like that from our sample package. And we just give this object that we created this split. So weather split, we just give that to training. If you run that and you print it, now this is an actual data frame, and this is your training data frame. We see here, I want you to notice, we still have the same number of columns. We have not changed that. But now we have 488 rows, which were randomly selected from your 698 rows. And as we saw here, we're getting 488 on this data frame for training because that's how many rows would go based on a 70-30% split. If you change this proportion to 0.8, you're doing an 80-20 split, and therefore the number of rows here are going to be different to reflect that. So the reason why we have 488 in train is because we're getting 70% of the total rows, which are 698. Yes? Maybe I didn't set the seed. Let me see. Maybe I just ran before. So if you just come and run the whole chunk, 488, is that what you did? You ran the whole chunk? Can you run that one more time? Like run the whole chunk, starting with set seed? Are you getting the same? The train?
And now it's.
Yeah, so maybe what could happen, maybe on my side or maybe on your side, if you just come here and don't set seed and just run this, then you may get a different result, right? So that's why setting seed and then running the whole chunk is making sure that you get reproducible results. All right, so we retrieved our train set. Now let's retrieve our testing set on the next chunk. So if you go there, we're gonna use a function called testing. And then similarly, just give it our weather split data frame there. If you run that and you print weather test, you should be seeing 210 rows. Again, the reason for that is because on your split, on your initial split here, we determined a 70-30 split, and that was saying that our testing is going to have 210 rows. So that is matching what we're getting here on the weather test. So we just made our split, right? We have our training data and our test data. And if you remember in lecture, we talked about data shift, which, I mean, it can happen from many different reasons, but one of the implications of that is, or one of the ways of checking for that is to check the distribution of your testing and your training data, especially related to your predicted variable. So I left you the code here. You don't have to do it, but I'm basically calling two geom densities. The first one is based on the weather train, so our training data, and I'm plotting a density for strength and coloring that in red. And then I'm asking for another geom density now on the test data and coloring that in blue. So if you run this, you should see something like this. Right, so what we're seeing is that the distribution of our predicted variable across our training and testing data, well, that's what we're seeing here. We see that their distribution, I mean, it's not bad, right? It could have been worse if you think that we just did a random sample, right? It was completely random which 30% went to training and 30 went to testing. So it's not bad. But I do want to show you how you could fix this if they were more mismatched, if there was not a good agreement between them. What could you do? So if you go back into your code, go back to your initial split function, there is an argument here called, let me just make sure I get the right name. I think it's called strata. Yeah, strata is the name of the argument. So you can really give any variable to strata, any variable in your data frame. In this case, I want to give our predicted variable, which is strength underscore GTEX. So if you give this and you run it, you're still going to get, well, I think now I got, well, let me make sure I run the whole chunk. So setting seed again. So I get 487 rows in training, 211 in testing. A little bit different number than before, but that's because it's doing a stratified sampling based on our predicted variable. If you read more in the documentation of initial split, it's going to explain to you how it's doing that. but it's basically creating, imagine that you have a distribution of your entire 698 rows of strength GTEx. It's basically creating bins of different quantiles across the distribution, and then doing the 70-30 within each bin. So making sure that the same proportion of different bins within your distribution are going to train and test. If you do not do stratified sampling, it could happen that just by random chance, you would get, like, let's say, really low values of strength in your testing and really medium and high values in your training, which is data shift. You have a different data distribution of your predicted variable across train and test. We do not want that. You want, again, your training and testing to have a similar data distribution of your predicted variable, so you make sure that you create a model that can predict unseen data. So by doing the stratified sampling on our predicted variable, so if you just rerun this whole chunk here, setting seed, making sure strata is implemented, you run again the weather train chunk, so it resets and gets the new train data points, and you run again the weather test as well, so you get the new test points. And then you just rerun this density plot. You're going to see that now they're going to match more closely, right? Because you're stratifying by your predicted variable, so you're making sure that they match more closely. Again, our previous split was, our previous run without stratifying was not terrible, but this is just a way you can ensure that you have a similar distribution across testing and training, which is important. All right, so now we're basically going to put our test data, our test set aside. If you remember, we only bring back the test set in the end, when we already train a model, we already know what model we want to use, and then we bring the test just to validate the model. So right now, we're going to forget about the test set and only keep working on the training set. All right, our next step here, we're still in that first step of processing. So we just did our split. Now we're going to do data processing as far as performing some steps here. We're going to help us. I'll be with you in a second, Comfort. They're going to help us to make sure our model, that our data fits the requirements of that specific model we're using. And we're going to talk more about that in a second here. But yes, Comfort, go ahead.
Thank you, Dr. Passos. I wanted to clarify something on the stratified sampling. So you advise that we use the stratified compared to the random sampling each time we want to do the ratio between the training and the test data sets. And also, is it always the predictor variable we use as the strata, or we can use any type? What if we have multiple predictors in our data sets?
Those are really great questions. Thanks, Comfort. So the first one, if I recommend using a stratified sample by the predicted variable, I don't see why not. And some people don't do it. So it's not a requirement that you do by the predicted variable, but I think it's a safeguard for when you're running a model, especially to make sure, again, that that predicted variable distribution is similar across training and testing. Because if it is not similar, it does not matter how much model training you do, you're not going to create a good model to predict unseen data if that unseen data is completely different from your training data, right? And I guess this conversation, of course, we're doing that here for a data set that we already have the whole data set, and we're splitting that between training and testing. But imagine that the goal of any machine learning model is for you to create predictive models that can predict new observations that the model did not see. In our case, that is our test set. But ideally, you could implement, like if you, in industry, for example, models are trained to then be applied to data that was not used in the training process at all, right? So maybe imagine if you have an AI algorithm that you're using somehow, the data you're providing or the question you're asking it, whatever you're doing, was not specifically something that the training set saw. But as long as it's still within the range of the distribution of the training set, is still valid. Now imagine, if you look here, just as another example to make this point, So our strength values are ranging from around 20 to maybe 37. If I have a new data set that has strength values of 40 or 45, which I don't even know if that's biologically possible, but just making something up here. If you have values that are really high, that were never seen by the training data or was not present in the training data, and therefore the model doesn't know how to handle them, it's probably not going to make a good prediction, right? So data shift could happen on the training and testing split, but it could also happen if you train a model on one set of data and then you try to predict on new data that is completely outside of the range. That's also data shift. You're also predicting to something that you don't know about. So I guess I would recommend that if we use this strata by the predicted variable, it just makes sure that you're not suffering from data shift, at least not from this purpose. But again, not everybody does it. It's not a requirement, but I think it's a good practice. Now, on the second question, Comfort, that you had, could you stratify by a predictor variable? And the answer is yes. So we're not going to see that in this class, but when you have, one example of this is when you have spatial temporal data, if you really want to make models that are very robust and that you are sure the model can predict, or you're given the best chances of the model being trained in a way that it can predict new data, perhaps we should stratify by year, or maybe stratify by site, or maybe some combination of those, or maybe, anything that you imagine, especially, okay, let me take one step back here. Especially if you have a predictor variable that is perhaps categorical and you do not have the same proportion of the classes. So let's say that we came here and we classified, let me just take a quick example here, taking one of these columns. If we took maybe, mean day length in January, regardless if that's an important variable or not. If we just use that and created a categorical variable out of that to say low, medium, and high. And let's say that we have a lot more values that are medium and high, and we have just a few values that are low. In that case, we could use this column and basically stratify by this predictor variable to make sure that both our training and testing have the same proportion of classes of the high, medium, and low classes in this case. If you did not stratify by that, what you may end up with is maybe because you only have very few low values in this data frame, just making that up, I'm not even sure that would be the case. But let's say that all your low values fall into your test sets. So the train set never sees a low value because there were so few in the overall data set that by random chance, they just fell into your test. So the training is never going to see a low value, and therefore will most likely not be able to predict well a low value on new data. So that would be an example where you may want to use some of your predictor variables to stratify by instead of a predicted variable. Does that make sense?
Yes, sir. Thank you.
Awesome. Thanks, Comfort. All right. So coming back here to data pre-processing, as we saw in class, some of the steps that you may want to do or may need to do depending on the model you're using are things like removing unimportant variables, performing PCA on the go, normalizing values, dropping NAs, removing columns with a single value, and there are other steps as well. So for that, we're going to create a recipe, which is basically a term that's very specific to tidy models on how we're going to handle this. And before we get into that, let me just take a quick step back here and tell you that we are training machine learning models with tidy models. That's what I decided to teach you because I think it connects well and it has a flow that makes sense, at least to me. There are other ways that you could be training machine learning models in R. You do not have to use tidy models. If you Google different models, machine learning in R, you're going to see different approaches to this. But again, I'm showing you an approach that is more consistent as you move from model to model in hopes that that's going to be easier to learn. But just as a FYI right there. And so tidy models have this concept of creating a recipe, which is what we're going to be doing next. You don't see this word specifically used in other workflows training models, but Tidy Models uses this, which I think is a useful analogy for us when we're doing this. So this recipe is going to include our pre-processing steps that we're going to be doing here, and it's going to apply that to the train data and can easily be applied to your test data at the end, very easily. So you create a recipe, you say what's going to happen, it applies that recipe to train independently and to test independently in the end. So it's an easy way to port your pre-processing steps across different data sets without needing to repeat the code and so on. So I have two links here that I want to show you. So one is that different model types will require different processing steps. Keep that in mind. That is really key. In our case, the model type that we're going to be running here is called linear reg for linear regression. And if you open this link here, it's one of the chapters from the Tidy Modeling with R ebook that I shared the link in class, in lecture. And it just has here a table with different model types and some of the recommended pre-processing steps. So our model that we're going to be using today is linear reg, so for linear regression. So it's saying here that we should create dummy variables. This applies when you have categorical predictor variables. We do not. All of our predictor variables are numerical, so we don't have to do that in this case. It recommends to apply a ZV, which is a step that stands for zero variance. This happens when you have a column in as a predictor that has one value only. So let's say that you had a column there that had a number 1 all the way down. There is zero variance in that column. Everything is the same. We don't have that in our data, so we don't have to worry about applying the zero variance step. It's recommending to apply some imputation step if you have NA in any of your columns. We do not have NAs in any of our columns, as we know, so we don't have to do the impute step because we don't have NAs. It's recommending to do a decorrelate, which is through PCA. We're gonna see this, and I will show you how to do it, even though I'm gonna ask we don't do it here because of a specific reason that you'll see in the end. But it is recommended to do a PCA if you're using linear reg. But interesting, if you look across this table, some of these steps are not required for some of these models. Some models require none of these steps to be applied. So it's really model specific. Keep that in mind. All right, so coming back to our code here. This may actually be a different. Or maybe not. Okay. All right, so coming back to our code, if you go on the weather recipe, that's where we're going to write our recipe. Just fix the size here. Well, and another link I want to show you, I'm not going to go there, but so on this first link I showed you shows a table with the name of the steps, but it didn't give you the functions to use. So if you go on this next URL I provided you here, you're going to see all the steps and the function names associated with those steps as a list on this link. All right, so let's go ahead and start our recipe that we're going to be applying here. So give it a assignment symbol. If you want to come after that first comment of defining the predicted and predictor variables, we're going to call a function called recipe, where we're basically going to give it a formula. We're going to say strength underscore dtext, which is our predicted variable, tilde, and then all of our predictor variables, which we have about like 74, I think, or 73, something like that. Instead of typing all of them, you can just come here and give it a dot. So a dot is basically going to say all the other columns in this data frame except strength should be placed here. So that's an easy way to say that. And then give it a comma. I'm breaking a line just to make it more readable. And we need to give what is the data that contains what is the data frame object that contains this data, which is called weather underscore training or train. Notice that we're given the training data in this recipe. All right, so we started the recipe. Here we're basically setting what's the predicted and predictor variables and where they're stored. Now we want to apply some of those steps. So give a pipe here, come after that comment. I want to remove some variables here for a specific reason. Maybe you're thinking, let's use a dplyr select. You could use that potentially, but we do want to use one of the functions that are within the scope of recipes, which is called step underscore rm for remove. So here I want to remove year and site because I don't want those to be there. I want the data to tell me the characteristics of years and sites. Because imagine it does not help you to create a predictive model that tells you that year is important and then everything before 2000 is one way and everything after is the other way. That makes no sense because new data is not going to be, well, most likely it will be future data, right? It's going to be something after you collected this data frame here. So let's include here year and site, remove those variables from our training set. And then if you remember, we talked about perhaps removing weather variables that represent data outside of the growing season. Because we would imagine, at least initially and theoretically, that weather variables that happen when the crop is actually growing are going to be important, but not the ones that happen when the crop is not growing anymore in the field. So we're going to use a function here. Maybe let's break line just to make it more readable. We're going to use a function called matches. And we're going to give here a pattern. So if you open and close quotation marks, I'm going to add the months that I want to remove. So any column that has the word Jan is going to be removed, but I want to give all the months that I want to remove, and I'm going to separate them by a vertical bar. So Jan, Feb, vertical bar, Mar for March, vertical bar, APR for April, vertical bar, Nov for November, vertical bar, DEC for December. Make sure you follow this pattern of uppercase first letter, and then so Jan, Feb, March, or Mar, APR, NOV, DEC. This is what's going to remove all columns that have these months as part of their name. And then lastly, so this model we're going to be using is asking for decorrelating the variables. I left you the code, but I want to ask you to just leave it commented off. I don't want to apply that, and I'll explain why in the end of this exercise. But if you were to apply this, you would just add a pipe here, uncomment the step PCA, and basically we're saying apply PCA to everything that's numeric except the outcomes. What is the outcome? The outcome is strength in GTEx. How does it know that strength GTEx is the outcome? It knows because you specified on this formula up here. Anything to the left of the tilde is outcome. Everything to the right is predictor, I guess is what it would call. So we're saying apply PCA to everything that's numeric except the outcome. And then I'm saying how many components I want to keep. If you remember from the PCA exercise, I think we needed 7 PCs to explain about 80% of the variability of the data set. That's why I'm putting 7 here. This could be 3, it could be 10, it could be 72, whatever you want, that makes sense. But as I told you, I do not want to apply PCA in this case, and you'll see why in the end. So just make sure you do not have a pipe after step RM, and you comment off this step PCA. If you run this, it actually failed on me. Could not find pipe. I thought I had loaded tidyverse.
Excuse me, Professor.
Yes.
So at the beginning, you don't have a pipe. You added that thing to name. So if you look at the first line, you'll understand what's the error. After weather recipe,
Okay.
this isn't it supposed to be a pipe?
No, so this should be an assignment symbol. Let me see what. Yeah, I'm not sure.
I think your environment is empty. So maybe this is the wrong part.
Yeah, that's right. I think I have two projects of the same. That's what's going on. I think this is not the one I was working with. So let me close this RStudio project and just go back to the one I had. Okay, yeah, I think this was my environment, so this should work. Okay, yeah. Thanks, Sumar. Thanks, Comfort, I think, helped me out here. Okay, so now we have our recipe. If you just print your recipe, you're gonna see here you have one outcome, 74 predictors, and the operations we're doing here are basically to remove variables year, site, and then it had many others that is just giving you as 3 dots there. All right, so now that we have our rest, so these are the steps we want to apply, but they have not been applied yet. So now we're basically gonna prepare our recipe, which if you come on the next chunk, we're gonna give the recipe object, so weather recipe, and then pipe that into a function called prep to prepare this recipe. So if you run that and you print weather prep, you're gonna see that now to still give us the outcome, 174 predictors. Training information is saying that we have 487 data points and no incomplete rows, so no NAs. And then it's saying train here. Notice on the right now it's saying that operations of removing ear, sight, and all the others, it's saying trained. So we basically applied the steps that we create on the recipe to the train data. So now the train data is ready for further training. All right, so we just finished that first step of doing our data split and pre-processing. Now we're gonna get into the training part of this exercise. So we are at 10:37. Maybe this is a good stopping point to give you a quick break. And then after that, after 5 minutes, we'll come back and start the training. So let me just set a timer here for 5 minutes and you can take a break. All right, let's continue with our exercise here. So we're starting on the training part of this exercise. We need to first specify our model. And so for that, here's where you determine first what model type you're going to use. Again, today we're doing elastic net. If you're doing a different model, let's say random forest, this is where that is going to differ. This is the step where you're going to specify your type of model and also what type of engine you want to use. So basically what happens here is even if you take one model type, let's take for example, random forest, which you're going to see when we do that exercise. If you do random forest in R, there may be 3, maybe even more packages that can implement random forest in R. Each package has their own way of specifying hyperparameters, different arguments, function names. Everything is a little bit different from one package to the other. What Tidy Models does for you is that you can specify the package you're using through the engine, but then Tidy Models make everything else standardized. Even if you're running random forest from package A or package B, if you do that through Tidy Models, the interface is the same. So another reason why Tidy Models helps us with that. If you're not, and again, you don't have to use Tidy Models, you can just do the other package by itself. But then the code is going to be different if you do random forest in package A versus package B. Tidy Models give us that consistency across different interfaces. And that's basically what the engine is you say what type of model, which would be, let's say, in the example, I'm giving you random forest, and then the engine is where I specify which package you're implementing random forest with. So that's what the engine is doing here for us. In our case, ElasticNet, it is a linear regression model, but penalized. So our model type is going to be linear regression, but then our engine is going to be specific to a penalized regression coming from the GLMNet package that you installed earlier today. That package is specifically, or this analysis in specific is going to have 2 different hyperparameters that we're going to be fine-tuning. One of them is penalty, which is equivalent to what lambda does, and the other one is mixture, that if this mixture value is equals to 0, then you're basically doing a ridge regression, and if mixture is equals to 1, you're doing a lasso regression, and you can be anywhere in between 0 and 1. So it's just how much of a mixture you're bringing from ridge and lasso into your model. Now, again, you could just come here and train a machine learning, or I guess it wouldn't be training necessarily, but it just run the machine learning model, giving you a fixed value of penalty, a fixed value of mixture. It would work, it would run for you, but there is no way that you can know if a different value would have been better. So that's when we fine-tune a model, is we let the data tell you what is the best value for each hyperparameter that we should use to optimize prediction. So we're going to fine-tune these hyperparameters here, which again are controlling model complexity. All right, so if you come here on the ENet spec is where we're going to specify our model type and engine. So give it the assignment symbol. If we come after that first comment, we're going to specify linear regression as the model type and ask it to tune specific hyperparameters. So we're going to use a function called linear_reg from the package parsnip. And here we're going to give the 2 hyperparameters that we can fine tune for this type of model elastic nets. One of them is called penalty. And we're going to type here a function called tune. Notice I'm not giving a value, I'm giving a function that is going to fine tune penalty for us. And then we're also going to give, ask for the argument mixture and also say equals to tune. So we're asking the model to tune both of those hyperparameters for us. We give it another pipe, come after that comment to specify the engine. And here we're going to call a function called set_engine. And in quotation marks, say GLMNet. So again, linear reg is the overall model type. The engine here is specifying which package specifically you want to use to apply that model type of linear reg. So if you run this and you print the ENet spec object, you're going to see this linear regression model specification. It's a regression type because it knows our Y variable is numerical. If our Y variable would have been categorical, this would say classification instead of regression. And then it has main arguments, penalty and mixture. And you can see that they right now have a placeholder for tune, which means we're going to fine tune them. And then it has the computational engine, GLM nets. That's the package we're going to be using in the backbone of this. All right, so we specified our model and our engine. Now we're going to do hyperparameter fine tuning. If you remember, well, there are two ways of doing fine tuning. One is to create a fixed grid, and the other one is to create a sequential search of a given grid. Today, we're going to implement the fixed grid approach. So I left you here the code already, where I'm basically creating so if you just look at penalty and you just run the sequence 0, 10 by 1, if we just run that, it's basically giving us the sequence, starting in 0, going to 10, in increments of 1. And then doing the same for mixture, starting at 0, going to 1 in increments of 0.1. And then I'm using the crossing function to get all potential combinations of all those values for penalty and mixture. If you run this code and you print the INET grid, you're going to see there is 121 combinations between all the values we created here for penalty and mixture. This is just what I decided to do. You could change here maybe your starting point and ending point, or even your step size for each one of the two. You could have more points in this grid. You could have less points on this grid. It's up to you. This is what I'm proposing for this exercise. So right now we have 121 pairs between different values of penalty and mixture. For us to visualize this, let's create a ggplot just so you see what's going to happen behind the scenes. So let's call here a ggplot. Our data is going to be equal to that INET grid object that we just created. On our AES, I want to put on the X equals to mixture, and on the Y equals to penalty, which are just the columns of that data frame we had above. And then add a plus, and let's add G on points. If you run that, this is our grid. So at each one of these pairs between mixture and penalty, we're going to be evaluating a model. So we're going to be running, I mean, you don't really feel it, I guess, because the coding is already pretty simple, but behind the scenes, it's going to be running many models for you. So basically, it's going to run all these models and then search for which one of them gives you the best R-square or RMSE. That's basically what we're doing here. So again, today we're using a fixed grid. We'll use a different type of approach in the next exercise, but I want to start simpler and build from there. All right, so we just created the grid, but we have not started our search yet. So to do the grid search, we need our model specification, which is the object INET spec that we already have. We need a recipe to be applied to the data with those processing steps, which we already have in the object weather recipe. We need a grid, which is the one that we just created, and it's assigned to the object INET grid. And we need a resampling strategy, which we do not have yet. So we still need to work on our resampling strategy. So if you remember, we have all the data was split between training and test. The test, we're not touching yet. We're just completely ignoring that for now. On the training set, now we're going to do resampling strategies to be able to better understand what hyperparameter values are better for our training set. So our training set now is further going to split into different folds. If you remember, we had a V fold was one of the strategies that we saw in lecture. So now we're going to create different folds of a given size, and each one of those folds is going to be trained at each point of the grid. And in the end, we're going to ask for R-square and RMSE on the assessment sets of the training sets for each one of the folds. I know that's a mouthful, but if you want a visual refresher of that, you can go back to the lectures and see what's going on there. All right, so I want to do a V-fold cross-validation approach here on the training set. Again, remember, this is not test set, just on the training. And for that, we're going to use a function called vfold_CV coming from the rsample package. We give here the data that we want to apply this, which is in the object weather underscore train. Again, notice we're giving the training set only. We're not giving the whole data set. It's just the train set. And then it has an argument for V, which is the number of folds you want to do. Let's do 10. 10 is a pretty common number of folds. So if you go ahead and run this, and you print this object here, this is what you're going to see. You basically have 10 rows because we ask for 10 folds. If you had asked for a different number of folds, you get that number of rows. So we have here 10 folds where in each one of those folds, 10% of our training data is going to be used for, well, let me rephrase that. In a 10-fold cross-validation, you take your training data, 90% of your rows are going to be used to train the model, that means applying that 90% of the data of your training set to each one of the combinations on your grid and getting then R-square and RMSE based on the assessment set, which is the other part of the fold. So the 10% remaining that you did not use for training. Again, if you need a visual refresher, go back to the lecture. I think it's going to help you to understand that. But that's basically what's going to happen here. If we just pull out the first fold on this under the splits, you're going to see that there are. So it's telling us that on that first fold, it has a total of 487 observations because that's the size of our training set, if you remember. And then for the training component of this fold, it has 438 of those observations and then 49 for the assessment. On the assessment here, these 49 is what is going to use to check for R-squared and RMSE of the predicted by observed to give you the best model. But it has this, and if you go to the second fold, so instead of the first, I check the second one, it has the same numbers, but it's going to be a slightly different data that goes into the training and into the assessment because they are switching the folds. So in each one of these iterations, one of the folds is kept for assessment and all the other folds are used for training. But then the one that was used for assessment on the first fold goes back and a different one comes out on each one of the folds. That's basically what's happening here.
Dr. Bustos.
Yes.
So this assessment is the validation, right?
Yeah.
Just a different term.
Right. Yeah, if you go back to the lecture, they use a different term there, or the source I use in lecture use a different term, but this is the validation. Yes, Ricky.
Thank you.
All right, so now we have everything we need. We have our model specification, our recipe, the grid, and the resampling strategy, which we just did below. So now let's combine all that into this function to do the grid search and give us a result. So if you come here, we're going to call a function called tune_grid, which we give the specification, which is in the model, which is in the object enet_spec. If I just print that, that was our model where we set the model type, we set the engine and the arguments we want to tune. The next thing we give it is it has a argument for preprocessor. This is your recipe. The recipe is under the object weather_recipe. We have an argument for grid. So grid is where you give the object that has the grid that you want to evaluate. That object name is enet_grid. And then lastly, it has an argument for resamples, which is where you give the object that has your resampling strategy, which is the one that we just created above, and that is called resampling _fold CV. Now we'll go ahead and run this. It's going to take a moment because again, it is, if you think about it, it is evaluating 121 combination of hyperparameters. Each one of those combinations is being evaluated 10 times. So it's basically running 1,210 models right now. So it takes a little while. It may take a minute or so, but it's basically doing that search for us. It's going to each point of the grid, evaluating each one of them 10 times, one for each fold, and then creating an R-squared and RMSE out of it. So mine just finished running. Perhaps yours may still be running, but hopefully not for too much longer. we got a warning here that there was a correlation computation is required, but estimate is constant. It has 0 standard deviation, resulting in a divide by 0 error. So returning an NA. Okay, so maybe some of those combinations of penalty and mixture were not able to be evaluated because it was given the same value for everything. That's just a warning, but we can just keep going. If you go ahead and print the ENAG grid results, this is what you see. You still have your 10 folds or 10 rows here, one for each fold. You have a dot matrix and a dot notes. So if you were to, let's take a look into this dot matrix. So if you just type again ENAG grid result, $, dot matrix, and let's pull the first one, just so we inspect that. So here we have, so on that first matrix of the first fold, we have 242 rows and 6 columns. You see there is a value for penalty, or there's a column for penalty, one for mixture, one for metric, one for the estimated type, one for the estimate, and then config. So what this is doing is basically for that first fold that had 90% of the training to train and 10% to assess, it basically calculated that fold was tested across all of your grid values, potential values, where we have the columns penalty and mixture. And each time it was testing one of those models, it was then extracting this estimate fit metric for you. In this case, that estimate is RMSE. So it got you the RMSE of your, for a model that has a penalty 0, mixture 0, applied to, applied to that combination of the grid, penalty 0, mixture 0 of the grid, and giving you this estimate, in this case, that estimate is RMSE, for predicting the assessment set of this fold. So we use the training part of the fold to train and the assessment to produce you these fit metrics. And there are, if you were to just keep scrolling down, we're going to see there are 2 fit metrics under this dot metric column. One is RMSE, the other is R squared. The reason why we have 240 rows under that first fold is because that first fold was 121 combinations of mixture and penalty times 2 assessment metrics. You have 2 metrics under this column, therefore you have 242 rows. And this is just for the first fold. You have 9 more, right? So it's really doing this in a lot of different models. Now we're going to collect a summary of these metrics across all folds and for each mixture and penalty combination and plot them. I left you most of the code. If you just go there, these 3 dots, so we're starting with the ENAG grid result, which is this object here that we just created above. We're going to call a function that is named collect underscore metrics. This is going to collect the RMSE and R squared metrics for across all folds and all the different combinations of mixture and penalty. If I just run this here, we have 242 rows again, because it's 121 for different combinations of penalty and mixture, and because we have 2 metrics. I'm just filtering the RMSE metric and then making a plot where I put penalty on X. And then now we have this mean value. So, okay, let me just take a quick moment. I forgot to mention this. So when you collect metrics, notice that now we have a mean of the RMSE for each combination of penalty and mixture. This mean value is the mean across all 10 folds. So now we're basically taking the average of each penalty and mixture combination across 10 folds and using that mean here as the metric. So I'm plotting that mean on the y-axis, and I'm just coloring based on the factor of mixture, creating a geom line and point. Let's just run that so you can see. What do I have?
I think we need to use a pipe after collect metrics.
Yes, thanks everyone. All right, if we do that, this is what you see. So basically we see here, we have penalty on the x-axis. Each line is a different mixture value. And we have RMSE in this case on the y-axis. With RMSE, do we want high or low RMSE?
Low.
Low, right? This is the error. So we want a low value. So just assessing here, it looks like having a penalty of maybe around 1 with, so right here, penalty of 1, and then a mixture of 0, it looks like, is this red line, gave us the best model. Those would be the combinations that we should choose, pretty much, if we use our MSE as the metric to decide. Now let's do the same thing, but look into R-square instead. So if you come to the next chunk, I think I left you everything. It's going to be the same plot, but looking at R-square. So in this case, we want high, right? Higher is better. So it looks like the highest R-square that we got was with a penalty of potentially around 1 as well, but a mixture of 0.1, it seems like. As you're seeing, there is a different, if you use our MSE as the metric, it gives you a different model as the best one when you compare it to using the R-square as the metric to decide. Normally, you would choose one of those metrics to be the one that tells you which model you want to go with. Perhaps there is a specific reason why you would choose one over the other, but normally, as long as you explain that you're using a given metric, you tell what it is, and you just go with that. That is probably sufficient if you're publishing as a paper. All right, now we are just visually assessing here what was the combination of mixture and penalty that gives us the best predictive model as assessed on your assessment set. Notice this, you have not used your test set yet. That is still in a drawer somewhere. So now we are actually going to extract the hyperparameters from the best model as judged by 2 different metrics, our MSE first. So if you come on this next chunk here, we're going to use a function called, or we're actually going to call first our object from the grid, which is called enet_grid_result. So the one that has the results of assessing all the combinations of hyperparameters. Give it a pipe, and we're going to call a function select best. Select_best. And here we need to say what metric we want to use to give us that result. So there's an argument for metric. I want to give in quotation marks our MSE. If you run that and you print the best RMSE, it's telling us here that the best model, in this case, the one that produced the lowest RMSE, has a penalty of 1 and a mixture of 0. Now let's do the same for R-square. Let's check if using a different metric provides the same or a different recommendation of the best model. So again, we do enet_grid_result and pipe that into a function called select_best again. Best, and we say metric equals RSQ for R-square. If you run that and you get your best model, now if we use R-square, the best model is being a penalty of 1 and a mixture of 0.1. If you are getting different values than me, it may be because so I guess for us to make sure we get all the same results, we should once we finish this script, we should all go and run the whole script as one thing to make sure that our set seed is set, but that different steps that have a random component are not repeated more than once. Because if you do run a chunk that has a random component more than once, then you are one step ahead on the seed than I am. Or maybe I am one step ahead of you if I did that on my side. So if you're getting slightly different results, it's probably because either I ran a chunk that had a random component more than once, or maybe you ran more than once. Could be both. I guess when I originally developed this script, this was what I was seeing as far as mixture and penalty based on RMSE and on mixture.
So, even though the 0.1 mixture has a slightly lower R-squared, it's saying it's better because it has a smaller penalty?
No, so here what we're looking at is basically looking at the plots that we created and just using the function is basically going through those values and telling the model that gave you the lowest RMSE. So in this case, here is the model that you had a penalty of 1 and mixture of 0. which is different from if you use a different metric, right? So looking at R squared, the best model would have a penalty of 1 and mixture of 0.1. So there is just the fact that these are two metrics that, I mean, they are dependent on each other to some level, but they're telling you different pieces of how well the model is performing. Sometimes they agree. Sometimes you check the best model on our RMSE, it's the same combination of hyperparameters if you check on the R squared. As we're seeing here, they're not agreeing. So then it becomes up to you as the researcher to decide which one of the metrics you would use, and then just select that combination based on that metric to keep going.
But I'm saying for R squared, in spite of the zero mixture having a slightly higher R squared than the 0.1 mixture. Like if you look.
So if we go at the graph,
The zero. Oh, mine's different.
is it different than mine?
Yeah.
Yeah.
Never mind.
Yeah, so that difference could be because, again, maybe I ran a chunk that had a random piece of it more than once and you didn't, or maybe you did and I didn't. Maybe that's where the mismatch could be. But really, like, for, because we're developing the code, we're running things maybe more than once as we're writing the code. But ideally, you would develop the code and then run as one independent thing, right? And then the results would most likely match between what I have and what you have. Yeah, so really when I was developing this and I ran as one thing, I got these best hyperparameter values instead. Based on RMSE, I got mixture of 0 and penalty of 0. Based on R squared, I got mixture of 0 and penalty of 0.7. I'm going to use those values instead, just because, in class I'm running chunks more than once, and maybe that's adding some randomness to my results, and maybe it's not what you're seeing on your side. So now we're basically going to specify what are the so this is the training. We just finished training. So the training is you evaluating a whole bunch of combinations of different hyperparameter values to see which one fits your data best, in the sense of which ones create the highest predictive performance as measured by R squared and RMSE. And remember, we have not used a test set yet. We have only used the train and partition that into different folds to then create these metrics. All right, so now that we trained, I want to basically use the fit metrics from the R squared, using R squared as the fit metric, and use those hyperparameter values to keep going. So if you come on the next chunk, we're going to call here the linear reg function. I want to say penalty. So before, when we use this, we use the function tune. But now we have tune already. We know what the value is. So for penalty, I want to use 0.7. And then for mixture, I want to use 0. And then again, we just want to pipe that into the set engine function to say the engine is glm net, like that. So notice that this piece of code that we just created is completely unaware of data, of training data, of anything else. We're just saying linear regression with these values of penalty and mixture and this engine. So now we're going to basically get the last fit of this model based on our data, on our training data, and then based on these trained values that we obtain from the training process. So here we're going to do something that, again, in tidy models, we're going to do our last fit. What does that mean? Getting the last fit means that we're going to train with the optimal hyperparameters, which are the ones we just described above, using those values on the entire training set. If you think about it, up until this point, the training set has been resampled. We have not used these hyperparameters in the entire training set yet. It was resampled in 10 folds, and we ran those 10 folds, which had just a portion of the training, and then another part of it was used for assessment. Now our last fit is going to take these hyperparameter values and fit the model one last time to the entire training set at once. And then based on that model, is going to use that model to now predict our test set to give us the actual predictive ability metrics of this model, actual R-square and RMSE on the test set. Notice we're just bringing test set at this stage. So if you come here on the final fit object, we're gonna give it the
Dr.
assignment.
Vistos,
Yes,
sorry to interrupt. Can I see the previous code chunk real quick? Shit.
Swabir, I saw that you raised your hand. Go ahead.
Yeah, I was also about to ask for the same thing that Shakin asked.
Okay, sounds good. All right, so let's keep going here. So again, let's do our final fit or last fit here. So we're gonna use a function called last_fit, where we need to give our final spec. And just to print here, the final spec is just when we said what is the function, what is the model type, what are the hyperparameter values we want to use to train, and what's the engine. That's all that it knows. It does not know any data. It does not know recipe. So the next thing we need to give it is the actual recipe, which is in an object called weather_recipe. And then we need to give the data split. So this is something that we did in the beginning of this exercise when we did that initial split to say what is training, what is testing. So we're gonna say here split equals to, and the object name is weather_split. So notice this is the first time we're bringing an object that contains the test set in it, the first time. If you run this, and then you run the final fit, collect predictions. So I'm basically collecting the predictions of the model that was used on the entire training set, but getting the predictions on the test set, which again is what we need here to assess model predictive ability. As you can tell here, we have 211 rows. Why is that? The test set, right? If you were to go all the way back, you would see that the test set has 211 rows. So these predictions here are based on the test sets. So we have a .pred column. This is the prediction from the model of what would be strength for the test set. And then we also have strength in GTEx, which is your actual observed data. This is what you brought into the model. So now you have your observed data and you have your predicted data on the test set, which again has not been seen by the model during training. Is independent of that. All right, so then let's get some metrics on the test set. So we're
Sorry,
going,
Dr. Vistos,
yes,
I'm sorry. I was getting an error on the final_fit, so
on the final fit object.
yeah.
Maybe.
It's like
So I think if you can look into the code and find what's going on, then great. But if not, I think I'm going to keep moving, but we can help you afterwards just to make sure that we can finish this exercise today.
okay, thank you.
Thanks, Shakir. All right, so let's get metrics on the test set. So what do I mean by that? Now I want to know what is the R-square and the RMSE on the test set, because that's what matters. That's what tells you the predictive ability of your model. So we're going to call a function, well, we're going to call the object final fit, which is what we just did above, and pipe that into the collect metrics function. So if you print that, this is what it gives us. On the test set, we have an RMSE of about 3 and an R-square of about 0.13. If you remember, now let's take one step back here. If you remember from when we did the multivariate exercise, and we did that correlation matrix, and one of the columns was strength explained by all these weather variables. I think the highest R-square was like 0.07, perhaps, if I remember well. It was lower than this, right? And I guess we would expect this to be a little bit higher because it's a multivariate analysis, right? We have many variables at play here, but that's basically what are our fit metrics on the test sets. Now, for curiosity and just, I mean, this is something you could report your R-square and RMSE on your train data. You can do that. The problem is when you only report that and you do not report the metrics on the test data. That's a problem. That's something you should be aware when you're reading machine learning papers as well. So here I just left you a whole bunch of code. I'm not going to walk you through that, but I'm basically getting the RMSE and R-square for the training data. If you just run that, we get here an RMSE of 2.85 and an R-square of almost 0.16. Now, how do these metrics compare to the test sets? If you just go back to the chunk up, what can you tell me about them, about each one of them individually? Okay, RMSE is smaller on the training set. Yes. What about R-square? It's higher, right? R-square is higher on the train set than in the test. This is it does not have to be this way, but it's very common to see this, where your model, you would expect your model to make better predictions on the train set because it was trained on that. It's like I give you an exam and before the exam, I send you the answers. You know the answers. You're coming ready. You know how to predict that to the best of your knowledge. So it is expected that the metrics on the train set to be better than on the test set, right? Because the model, when we built the model, when we trained the model, it was unaware of the test set data. It had not seen that data. So it's new information for the model. It can give you predictions both on the train and on the test, but the test performance is what we really use, or the test metrics are what we use to assess performance. All right, so remember that I told you that regardless of how simple or complex a machine learning model is, you should always be expecting to see a predicted by observed plot, especially on the test set, which is what we're going to do here. So I left you most of the code. So if you go to the next chunk and remove those 3 dots on the first row or the second row of the chunk, let's call here the function collect_predictions. If you just run final fit and collect predictions, so not the whole chunk yet, and you inspect the columns, we have the .pred, we have strength. So on the x-axis, you're going to have to type with me. I want to put strength on the x-axis. Strength, text, and on the y, I want to put the predicted. So .pred is the name of the column. You have a geom point. I have another geom here. So if you run into geom point and ignore that plus after geom point, just to see what happens. Oh, I forgot my pipe. Forgetting my pipes today. All right, so now it should work. You're going to see a scatter plot like this. Now, something that's very informative in a predicted by observed plot is to have the one-to-one line. So we're going to add the one-to-one line. Right after geom point, I have a geom, 3 dots. There's a geom for AB line, which adds a one-to-one line to your plots. So if you go ahead and just run the whole thing, this is what you would see. So the black line is the one-to-one line. And then we have strength on the x-axis and the predicted value coming from the model on the y-axis. And this is only on the test set. Remember that. As we see, maybe a range of strength between, I don't know, 27 to 32 is okay-ish predicted. But when you have high strength values and low strength values, the model is not doing a good job. What you would like to see is if these points were really close to the one-to-one line, meaning that what was observed is very close to what the model was predicting. In our case, it's okay-ish. And we were kind of expecting that based on the R-square. The R-square of this is 0.13, right? So we would not expect to have a very high correlation here based on our R-square. But again, predicted by observed plots, This is what you're seeing in front of you. You should always be expecting to see something like this in a machine learning paper, because giving you an R-squared and RMSE are good metrics, but this visual assessment and understanding is important as well. Even though that R-squared and RMSE are coming from this blue line, but seeing the plot is more important, at least I think, to understand the shortcomings of the model. All right, we're almost at the end here. So the next thing, let's see if I gave you everything. No. So we're using the final spec, which again is just the specifying the model type, the engine, and the specific trained hyperparameter values. We're using the fit function to actually fit that. And we're using here on data, we're using the bake function, which is basically taking our whole weather data set and applying the recipe, the prepare recipe to it. So a lot of things, but if you just run that, it's actually going to give you the results of your model that we can extract your coefficients from that model. If we pipe this into a function called tidy, it's going to make this tidy. So it's going to give us a slope coefficient under the estimate for each one of your predictor variables in this model. Now, if we come here, I just want to arrange this, the sort using the arrange function, using the descending order, so desk of the estimate. So we can see which estimates here had a higher impact. At least in this case, going from positive to negative, from high to low. So we see that at least on the high side, the minimum temperature in September had a very high coefficient in this model, which probably means it has a large impact. Among all the other variables, is one of the ones that has a large impact on strength, on predicting strength. All right, if you come to the next chunk here, is going to be our last chunk. I basically want to make a plot of the most important variables to show here. I left you, so it's still getting the final spec, fitting that into using the fit function. And on those three dots, I just want you to type the function VI. So this function is coming from the VIP package to show us variable importance. If you run until the VI and don't keep going after that, you're just going to see that it's going to be pretty similar, giving us the variable, the coefficients, and then whether that coefficient was positive or negative. Then we're just plotting all that.
Oh, yeah.
So, all right, so if you just plot all that, it's basically showing you this. So the importance of different variables in your model and whether or not they have a negative or a positive effect on the strength. So what I'm seeing on my side, it may be a little bit different on yours, again, because probably I got out of our seed by rerunning something more than once. But on my side, I see minimum temperature in September having a positive effect. So maybe the higher was the minimum temperature during December, the average had a positive effect on fiber strength. The minimum temperature in May, also a positive effect. And maybe the maximum temperature in July and September having a negative effect. So if you the high temperature within a day and then average over all days in those months, if that value, as that value increases, you are decreasing fiber strength. So this is a plot that you may see depending on the machine learning model. A variable importance type of plot is also very common. Yes.
Please, can I look at the code, the last code once again?
This one here. So all we changed was this line of code. All right, we have 3 minutes. So I just want to run you through a quick summary, which has a lot of stuff that we did today. And then, you can claim your attendance. I think, Aminder, have you opened? Okay, so claim your attendance. After we go through the summary, you are dismissed. And if you want to stick around for a few questions, you're welcome to do that. But basically today, we cover what are penalized linear regression models, We talked about Ridge, Lasso, and Elastic Net, which is a combination of both. We set up a machine learning workflow to train an Elastic Net model. We use the recipes to process the data. We use R samples package to split the data. We use a fixed grid to search for the best value of mixture and penalty, and we determine how many types of combinations we wanted to look into. We use a 10-fold, actually not a 5-fold, cross-validation as the resampling method. We assessed both the R-square and the RMSE of these metrics on the training data only, on different folds of the training data, to select the best model. Once the final model was determined, or once the best hyperparameter values of the best model were determined, we used that to predict on the test set. So again, notice the test set only came at the end. And then we evaluated that model on the test set by looking at the predicted by observed plots, the fit metrics of R-square and RMSE, and also variable importance. Excuse me. All right. So that's all we did today. Again, we're really close to being done. We have a couple minutes, but before you go, make sure you claim your attendance. Also, make sure you save your script. And then we do all the process of staging, committing. So let's just stage, commit. We can say we finish Elastic Net. And then push. So these changes are reflected on your GitHub repo. And then I'll be glad to answer any questions if you may have. And if not, then you are dismissed.
Dr. Vistos.